Hi guys, this is Dr. G here, and in this video we are going to talk about acetylide anion. Okay, so we will basically talk about alkyne acidity, which means we will talk about the formation of the acetylide anion, and also we will talk about a very important reaction that acetylide anion display, which is basically alkylation of acetylide anion. Okay, so in this video we will talk about a reaction that is associated to acetylide anion, and of course the formation of the acetylide anion and the acidity of alkynes. Okay, so if you remember the alkene and alkane lectures, okay, you understand that it is very difficult to remove a hydrogen. It is very difficult to remove a hydrogen from a sp3 or sp2 hybridized carbons, right? But in alkynes, you have an sp hybridized carbon, or in fact, you have two sp hybridized carbons. So if you have a terminal alkyne, one of these sp hybridized carbons will have a hydrogen. So when you have a terminal alkyne group, that hydrogen could be slightly acidic. Slightly acidic. So by using a very strong base, you may be able to deprotonate the alkyne hydrogens. Of course, you need to have a very strong base. So the base of choice in here is something like NaNH2. Okay, NaNH2 is a very common base that we use for this reaction, and then you will be able to deprotonate a terminal alkyne, generating an acetylide anion. Okay, this right here is called the acetylide anion. The unique thing about this anion is that you have your two sp hybridized carbons, and then one of those carbons will have a negative charge. So that is the unique thing about this reaction. It will deprotonate a terminal alkyne carbon. All right, so let's talk about the acidity of hydrocarbons. As you know, we never talked about this deprotonation reaction for alkanes or alkenes. Why? Because if you want to deprotonate a hydrogen from alkene or alkane, you need to have an extremely powerful base. In fact, if you talk about the pKa of alkene and alkene has the pKa around 40s, and then alkanes have a pKa of around 60s. So they are extremely weak acids. So it is very hard to find a base that is extremely strong, so that they can convince the alkanes or alkenes to lose a proton. But when it comes to alkynes, as you can see, pKa is still high. Okay, it is around 25, but it is manageable. Okay, it is manageable. So you can find very strong bases which will be able to deprotonate an alkyne. Okay, an alkyne. So the reason behind this acidity or the change in pKa is the stability of the acetylide anion. Of course, as you can see, when you go from an alkyl anion to a vinylic anion to an acetylide anion, okay, the negative charge is going to be on a sp3 hybridized orbital, sp2 hybridized orbital, or a sp hybridized orbital. And when you are going from left to right, as you can see, this orbital is going to increase the s character. Okay, so for alkyl anions you have 25% s character, for vinylic anions you have 33% s character, but acetylide anion sp orbital has 50% s character. So when you increase the s character, the stability of the negative charge is going to be increased. That is why by using a very strong base like NaNH2, you can deprotonate a terminal alkyne. Okay, that is why you can deprotonate a terminal alkyne. All right, so let's quickly do this worked example. You might want to pause the video and then see if you could do this. And in a second, I will give you the answer. All right, in this worked example, I'm telling you the pKa of acetone is 19.3. Okay, so acetone is having a pKa of 19.3. So it is a very weak acid. It is a very weak acid. So they are asking us which of the following bases is strong enough to deprotonate acetone. Okay, so acetone has a very uh, weak pKa value or a very high pKa value. So if you are using a base to deprotonate acetone, you better have a very strong base. That is the point, right? So in here you are given 4 choices, and if you look at pKa values for these 4 bases, of course the pKa value of the acid molecule, okay, you have the conjugate bases and acids. So the pKa values, as you can see, the only pKa value that is greater than 19.3 is B, which is the acetylide anion, right? So since the pKa of the acetylide anion or ethyne molecule is 25, which means it is greater than 19, so the deprotonated acetylide anion is actually a stronger base which can deprotonate acetone. So your answer will be B. Okay, your answer will be B. Remember, when you have the acid and a conjugate base pair, okay, if you have a strong acid, the conjugated base is going to be weak. But if you have a weaker acid, then the conjugate base is going to be stronger. Okay, that is the argument. Okay, so when you are looking at the pKa's, you want to make sure the pKa value is greater than 19.3. In fact, it is better if it is, let's say, at least the Ka value is at least 10 to the power 4 times, which means pKa value is around 4 numbers greater than 19.3. Okay, all right, so this is your solution. But here comes the more important part, okay, the reaction that we would like to learn in this video, which is the alkylation of acetylide anion. Why this reaction is important? This reaction is important mainly because this reaction can increase the number of carbons in your product. Okay, so in organic chemistry, these type of reactions where you can increase the number of carbons in your product is very important. Why? Because naturally, when you are buying molecules or when you are buying chemicals, it is cheaper to buy smaller molecules, and then uh, most of the times the drugs or the chemicals that you want to generate from those chemicals will have more complicated chemical structures, right? Which means you have to add carbons to your starting material, right? So the reactions which are capable of adding carbons therefore are very important. Okay, so this alkylation reaction is very important because it will increase the number of carbons in your starting material or in your compound. Okay, so let's take a look at it. In here, the acetylide anion is a negative ion, so it acts as a nucleophile. It acts as a nucleophile. Okay, and uh, when you have a alkyl halide next to you, okay, especially a primary alkyl halide, that is important. When you have a primary alkyl halide with an acetylide ion, it will go through a substitution type reaction. It will go through a substitution type reaction and it will give you a product. Okay, it will give you a product. Let's analyze this reaction. Let's analyze this sample reaction. So in here, I have used a primary alkyl halide, of course. Okay, and the leaving group in the alkyl halide is bromine. Okay, and the incoming group is, of course, our nucleophile, the acetylide anion. Okay, so in this reaction, what has happened is that the bromide has left, and then the acetylide anion has taken or attached to the alkyl halide carbon. Am I correct? Yes, that is exactly what is happening. So this is a substitution reaction. The nucleophile is substituting the bromide. The nucleophile is substituting the bromide. So if you are not very familiar with substitution reactions, okay, in later chapters we will talk about many different reactions for substitutions, okay, and then we will categorize them into different groups like substitution 1, SN1, SN2. But let's say that you don't understand them at this level. Okay, so in here this is like, these substitution reactions are like, divorcing someone and get remarrying someone else, right? So you're basically substituting your partner, let's say. Okay, in here you are substituting a halide with the acetylide anion, right? So that is like a divorce and second marriage, right? So when you are divorcing someone and remarrying, you can do it in two different ways. Okay, you can start an affair and then you can divorce a person, and then at the same time you can start a new relationship. So those two can happen at the same time. Okay, or you can first divorce and then find a nice person and then marry. Okay, but this reaction falls under the first category, which means, the removal of the leaving group and the addition of the new incoming nucleophile happens at the same time. So the removal, let's call it number one, or let's call it A, removal and addition, A and B steps, they happen at the same time. Okay, they happen at the same time. That is why you need a primary alkyl halide. That is why you need a primary alkyl halide. The thing about primary alkyl halides is that the carbon, the carbon that has the leaving group is not crowded, so primary alkyl halide carbons are not crowded, so therefore the nucleophile can easily attack that carbon. Okay, if the carbon is crowded, then it is very difficult for the nucleophile to reach that carbon. That is why you prefer primary alkyl halides. Okay, and then what happens in this reaction is that you will substitute the halide with a acetylide anion. Okay, so here is the mechanism, by the way. Okay, you can take a look at it in more detail, okay, if you want to. So basically the removal and the addition will happen at the same time. Okay, so the bromide will leave and the acetylide anion will attack at the same time. So it will go through a transition state that is given in this picture, okay, in this figure. As you can see, the breaking of the carbon bromine bond and the making of the carbon carbon bond will happen at the same time. Okay, at the same time, and then you will get the final product. Okay, so in here there is something called inversion of configuration. Okay, inversion of configuration. So basically, since bromide is covering this side, the nucleophile should come from the opposite side, right? Nucleophile should come from the opposite side. So if you consider this carbon, tetrahedral carbon, this one right here, as an umbrella, okay, because of this attachment of the nucleophile, the umbrella will flip to the opposite side, right? It will flip to the opposite side. So in the future we will talk about this inversion of configuration in more detail. Okay, but for now this is how it happens. Okay, this is how it happens. So by using this reaction, you can easily increase the number of carbons in your starting material. You can easily increase the number of carbons in your starting material. So let's look at this sample example that you have in this slide. So here you have a terminal alkyne. By using NaNH2 and ammonia, you will remove this hydrogen, and then you will make the anion, which is the nucleophile that we need. And then by using a primary alkyl halide, you will basically increase the number of carbons you have. Okay, so you can do this in two different steps, and that is how it happens. Okay, so let's take another example. Okay, let's say you have an acetylide anion like this, 1-pentyne. Okay, so in the first step, what we do is we use NaNH2. If you use that, we are deprotonating our alkyne, forming an anion, forming an acetylide anion. Okay, and then what happens is that if you treat it with, let's say, an alkyl halide, okay, so we want a primary alkyl halide. So here is our primary alkyl halide. Okay, this is a primary alkyl halide. Then what you get is the same alkyne group, and then you will add the R group of the alkyl halide. So let me use a different color, okay, so that it will be a little bit more clear for you. Okay, so I'm going to use the black color to show you where the incoming R group is. Okay, so you have a incoming R group like this, so it will be like this. All right, so if you want me to label the carbons, let's call this carbon as number 1, 2, 3, and 3 dash. Okay, you have 4 carbons, so this will be number 1 carbon, this will be number 2 carbon, this will be 3 and 3 dash. Okay, so those are the carbons. I hope you understand it. Okay, that is how it happens. All right, let's go back to our lecture note. By the way, this reaction is very important. Okay, so if you have acetylene, that means you only have 2 carbons in your alkyne, which means you have 2 acidic protons. So basically you can remove 1 proton and then attach an R group. Okay, attach a certain R group, okay, using the same reaction that we learned. Okay, and then you can again remove this hydrogen in the next step, and then you can add a new R group if you want to. Okay, so you can get asymmetrical alkynes at the same time. Okay, so that is important to know. And here is another example. Let's say I was making this primary alkyl halide so important before. Okay, I told you in this reaction, according to the mechanism, okay, for this substitution reaction to happen, the alkyl halide carbon should be less crowded. That is why we prefer primary alkyl halides, right? I told you that. Okay, so you are always using primary alkyl halides. But what happens if you use a secondary alkyl halide? So here is an example. Okay, you will learn about these mechanisms in much more detail in a later chapter. In fact, the next chapter. Okay, so you will understand them better. But let's say you are using a secondary alkyl halide. Okay, like the one that we have here, bromocyclohexane. Okay, so that is a secondary alkyl halide. And here is our nucleophile. Okay, same old anion. Okay, and in here now, because of the secondary carbon that you have in this alkyl halide, the nucleophile has a hard time reaching from the back door. Okay, it has a hard time approaching the carbon. So rather than giving you the extended carbon product, which is the one that we saw before, rather than giving you the extended carbon product, the alkylated product, in here what happens is that this acetylide anion will act as a base, and then it will remove an HBr. Okay, it will remove an HBr and will give you an alkene as the product. Okay, so we learned about this reaction in alkene synthesis. In the alkene synthesis, if we have an alkyl halide, by using a strong base, you can make a double bond, right? We can make an alkene. So in here, that is exactly what happens. Okay, that is exactly what happens. So rather than giving you the alkylation, it will give you an elimination product, which means an alkene. Okay, so that is the difference. So make sure to use a primary alkyl halide in this reaction. I think I have a worked example. So by now you know that you need to pause the video and try this by yourself before me explaining this. All right. So in here you need to prepare cis-2-butene using propene and alkyl halide. Okay. All right. So in here you are going to need to prepare cis-2-butene. So first of all, write cis-2-butene. Okay. Butene. How many carbons do you have in butene? You have 4 carbons, right? You have 4 carbons. So you are going to need 4 carbons. Okay, you are going to need 4 carbons, and then it is a cis. I mean, the double bond is in the second carbon. So 1, 2. Okay, here is your double bond, and it is a cis. So the 2 hydrogens should be on the same side. Okay, the 2 hydrogens should be on the same side. So this will be your starting material. Prepare, you want to sorry, this is your product. So you want to prepare cis 2 butene using propyne. Okay, propyne is what? Propyne is a 3 carbon alkyne, okay, which is this one. Okay, so this is propyne. And also you can use an alkyl halide. Preferably you need a primary alkyl halide, so you need something like this. Okay, something like this. So this is what you need to do. Okay, this is what you need to do. You want to use propyne, which is this one. Okay, this is A. You need to use A and B, an alkyl halide, and try to synthesize a 2-cis butane. This is what you need to do in this reaction. So how do you do this? This is very straightforward. So let's talk about the difference in carbon number. Okay, let's talk about the difference in carbon number. Okay, you have 1, 2, 3 carbons here in your starting material. In your product you have 1, 2, 3, 4 carbons. Oh, so in your product you have 1 extra carbon. Which means you have to use an alkyl halide which will have 1 carbon. So this R group is what? This R group is a hydrogen. Okay, this R group is a hydrogen. So let's do this. Let me erase everything. Okay, so we are going to start with our propyne. Here is our propyne, and to this propyne we will deprotonate using NaNH2, of course. That will be our first step. And in the second step we will use an alkyl halide with 1 carbon, which is CH3Br. Okay, and then you can use a solvent. I mean, let's not worry about it at this moment. And you will get 4 carbons, right? So your product will have 4 carbons. Okay, but now we have 4 carbons, but this is not the final product. We need to make it a cis alkene. Okay, we need to make it a cis alkene. So how do you get a cis alkene from an alkyne? We learned from a previous lesson. You have to reduce it using hydrogen, and you have to use a specific catalyst called Lindlar catalyst. Okay, if you use these two, your alkyne will be converted to a double bond. Okay, so this is your cis butene. All right, so this is how you do it. All right, guys, with that worked example, I'm going to stop this video. Okay, and I will meet you in the next lesson. Okay, you guys have a good one. Take care, guys.